So this is going to be a video walkthrough on how to solve a Buckingham Pi theorem problem. And for this problem, we are given a problem statement which says, small droplets of liquid are formed when a liquid jet breaks up in spray and fuel injection processes. The resulting droplet diameter, lowercase d, is thought to depend on the liquid density, rho, viscosity, mu, surface tension, sigma, as well as jet speed, v, and diameter, capital D. How many dimensionless ratios are required to characterize this process and determine these ratios? So the first step in this problem is going to be to determine the functional relationship between our dependent variable and our independent variables. And for each step in this, I have already gone through and solved all of them, and I'm just going to walk you through. So scroll down. Here is going to be what your functional relationship setup is going to look like. We have our dependent variable. This is lowercase d. That is the droplet diameter, and that's going to be equal to some function, which we don't at this point know what it is, and that function is dependent on the other dependent variables, which is going to be density rho, viscosity mu, surface tension sigma, jet speed v, and diameter capital D. I believe it's diameter of the nozzle. So steps 2 in this problem solving process is going to be to determine the primary dimension of each of these variables. And for this problem, we're using the MLT system. So we want to get every single variable, dependent and independent, in terms of either mass, length, time, or in some cases temperature. In this problem, we don't have any temperature, so we're just going to use ML and T. Starting with our dependent variable, D, that is here. That is going to be a diameter, which is a dimension of length. So we're just going to put L for that one. Now moving to the independent variables, we have rho, that's density. Density is going to be mass per unit volume. So it's going to be M over L to the third, or length to the third. And if we write that as a power, as you see here, it's going to be ml to the minus 3. And this is typically the most usable way to write them as you get more and more complex terms or start combining them. Now for viscosity, viscosity in SI has units of newtons times seconds over meter squared. Sometimes if it's a variable that you're not sure about, it's best to go to the unit and then work back to the dimension. So in SI, we have newtons times seconds over meter squared. Breaking newtons up, here we have kilograms times meter per second squared times seconds over meter squared. Now we write the primary dimension of all of those terms. Dimension mass, L, T squared, T, and over L squared. The next step, I find this to be useful, and you don't necessarily have to do this. It's kind of based on how complex the unit is or how many different dimensions you're adding together. But I like to write them as single fractions like this rather than a group over another group. This way, it makes it very easy to see which ones cancel out. So for instance, for M, we just write it as M over 1. For our LT term here, or L over T squared, we write that L over T squared. For our T term, again, T over 1, and for the final L squared term, we write that as 1 over L squared. And this way, it's very easy to see which terms cancel out. So right away, we can see that the L is going to cancel the L squared term, the T is going to cancel the T squared term, and that leaves us with M, still have that, M power 1, L power minus 1, T power minus 1. So that is going to be our dimension of viscosity. Next, we have the surface tension sigma. Now, surface tension is units of force over units of length. So again, in SI, that would be newtons over meters. Breaking newtons again with kilograms times meter per second squared. And then writing those as primary dimension. I have dimension mass, length, time squared, all over length for that M term on the bottom. And again, writing it as single fractions like this, again, it's easy to see which ones cancel out. So right away, we're going to see L cancels out, a T in the numerator, we don't have any M in the denominator. So our final unit for this is going to be MT to the power minus 2. Now for the jet speed, that is going to be a velocity. Velocity in SI is going to be units of meters per second, which is a dimension of length over a dimension of time. So this one, nothing cancels out, so we just have L, T to the minus 1. And then finally, we have the diameter, capital D, I believe that is the nozzle diameter, and that is going to be a dimension of length. So at this point, we've got all of our independent and dependent variables in terms of their primary dimensions. Third step in this problem solving process is going to be to determine the number of pi groups we're going to generate. Now the pi groups are going to be groups of these variables that we're going to make dimensionless. So I've already gone ahead and done that. And this is what you see here. So for step 3, we're going to determine the number of pi groups, or pi terms, sometimes they're called. Now, we're going to let n equal the total number of variables. So this is going to be everything from our dependent variable as well as all of our independent variables. So we're going to have 6 total variables. That's going to be n. M is going to be the number of primary dimensions we have. In this case, it's going to be m, l, and t. So we have 3 primary dimensions. This results in n minus m pi terms. That means we got 6 minus 3. That is equal to 3 total pi terms. So that's how many terms we're going to actually generate. So the last step before we can start generating our dimensionless pi groups or pi terms is going to be to pick our scaling variables. And the number of scaling variables is determined by the number of primary dimensions we're using. So again, in the MLT system, we have mass, length, and time. We're not using any temperature. That's denoted by theta. So we're going to have 3 scaling variables. Now, there's not an exact criteria for how we pick the scaling variables, but there are some general guidelines to follow. We don't want to pick our dependent variable d. Viscosity also seems to be one that tends to create some weird problems. Sometimes it won't cancel out. So in this case, we've picked rho, v, and d. Those are going to be our scaling variables. So that's what you're going to see here. We got rho, v, d as our scaling variables. That means the remaining terms are going to be our non-scaling variables. And those are the terms which we are going to make dimensionless. The 5th step in this process is going to be to make our non-scaling variables dimensionless by multiplying them by our scaling variables to some power. And the power is what we actually have to find. And the way the general setup works is it's going to be like this. You're going to start with taking your non-scaling variable. In this case, we'll start with the dependent variable, lowercase d. We write that as times our scaling variables, and we write each of the scaling variables to some unknown power. In this case, it's a, b, and c. Then we rewrite the same thing, but we do it in terms of their dimensions. So dimension of lowercase d is just length. Dimension of rho is ml to the minus 3. And we write that as power a. For v, we have l t to the minus 1, power b, and l power 1 to the c. Then we want to set up our primary dimensions just like this, m, l, and t. And we're going to start tallying which ones have these primary dimensions. So this first column here, this is going to be the column for our non-scaling variable. In this case, we don't have an m term, we don't have a t term, so these are going to both be 0. We do have an l, power 1, so we're just going to put a 1 there. Now for the other terms, our scaling variables, these each have these a, b, and c powers outside of the dimension. So in this case, we have an m term here, that is m power 1. We're going to write that as plus a. For l, we have l power minus 3, so we're going to write that as minus 3a. And then we do not have a t term for the density, so this is going to be 0 for the t term. We go down to the next. Next, for our jet speed, here, we do not have an m term, so that's going to be 0. And we do have an l, that's power 1, so we're going to write plus b here. And we have a t to the power minus 1, so we're going to write minus b. And then finally, for our diameter d, which is dimension length, we don't have an m term, we don't have a t term, so that's going to be 0. And this is also going to be 0. For the l, we're going to write it as plus c. Now, we've basically set up a linear system of equations. We want to set all of these equal to 0, and we want to solve for these constants, a, b, and c. And sometimes it's very easy to go right away. Sometimes it's more complex, and you could use a matrix to solve it. There's lots of different ways to solve linear systems, but in this case, we end up with a is equal to 0, c is equal to -1, b is equal to 0. The last step when you're making these pi groups is going to be to rewrite the equation that we started with here, this general relationship. We're going to rewrite it with our new powers, a, b, and c, that we found over here. So we're going to have rho, which was power a is 0, so we have rho to the 0, v is b, B is also 0, so we're going to say v to the 0 term here. And then d was to the power c. C is minus 1, so we're going to put a minus 1 for the d. This term's going to go away. This one's going to go away because they're both to the 0 power. Anything to the 0 is 1. And then for the d term, d is minus 1, so that's to say 1 over d. So we can rewrite our relationship between lowercase d and uppercase d as lowercase d over capital D. This is our first pi term. So we're going to say that that is equal to pi 1. These are generally, the pi terms are generally denoted with a capital pi. We're now going to move on to our next non-scaling variable. In this case, it's going to be viscosity mu. We write this in the same fashion we did before, where it's mu times our scaling variables, rho, v, and d, to the powers a, b, and c. Follow the same steps as we did before. And again, we already found these dimensions. So that's the whole point of finding the dimensions first, is it makes the rest of the algebra very easy. We've got our dimension of mu, we've got our dimension of rho, dimension of d, or v, excuse me, and our dimension of d. We have these each to power a, power b, and power c. Again, write our primary dimensions just like this, and we start tallying. So this first column is going to be for our non-scaling variable. In this case, we have an m term, we've got an L to the minus 1, so we write minus 1, and we've got a T to the minus 1, so we write minus 1. Moving down the line again, we have A for an M here, power A. We've got minus 3L here, so we're going to write minus 3A. We don't have a T term, so it's 0 here. Now we'll do the jet speed term V. V does not have an M term, so that's going to be 0. V does have an L, power 1, so that's going to be plus B. And it does have a T, T power minus 1, so that's going to be minus B. And then finally, the capital D, that's going to be L, power C. We don't have an M, so that's 0. We don't have a T, that's 0. And that's going to be plus C. Now, same thing, we write these all equal to 0, and we solve for our unknowns. In this case, A is going to be minus 1, C is going to be minus 1, and B is going to be minus 1. Now, just like we did with the previous pi term for pi 2, we're going to write this group just how we did here, but now with our constants or powers, which we have solved for. So we've got mu times rho to the A. A is minus 1, so we put a minus 1 there. V is power B. B is a minus 1, so we write minus 1 here. And D also minus 1, because that's C, and we write it as minus 1. That is to say, mu is going to go over all of those terms. It's 1 over each of these terms, and that is going to be equal to pi 2. Now, this may not be obvious right away, but this is actually the Reynolds number. It's just inverted. So it's 1 over the Reynolds number. And a unique thing of these pi groups is they can either be to a positive 1 power, or it could be to a minus 1 power. So there's no problem taking a pi term and flipping it upside down. And sometimes that is helpful because you can see these common quantities like a Reynolds number, which is going to be rho VD over mu. This is one that comes up a lot in fluid mechanics classes. So we're just going to write it like this. Pi 2 is equal to rho VD over mu, or pi 2 is equal to the Reynolds number. Moving on to our third and final non-scaling variable. And remember, we have the same number of pi groups as we determined in, I believe it was step 3. We have n minus n pi terms. So we are going to have 3 pi terms. We've already found pi 1 and pi 2. Now our step is going to be to find pi 3. So that, the non-scaling variable, in this case is going to be sigma. That's the surface tension. We follow the same procedural steps. We write it multiplied by our scaling variables to the powers A, B, and C. We write our dimensions out for each term like this, and then we set up our primary dimensions here, and we start tallying the terms to build this linear system of equations. So this first column, this is for our non-scaling variable. In this case, we do have 1m. We have a t to the power minus 2, so we're going to put minus 2 here. We do not have an L term, so that is going to be 0. Moving down the line, rho is going to have m1, so that's going to be a. L to the minus 3 power, so that's going to be minus 3a. No t term, so that's 0. Next up is going to be our jet speed term v. We do not have an m term here, so that's 0. We do have an L term, it's L to the power 1, so we're going to write that as plus B. And we do have a T term to the minus 1, so that's going to be minus B. And then finally, the diameter capital D is going to be L to the C here, so we don't have an M term, that's 0. We don't have a T term, that's 0. It's just L power C, so that's going to be a plus C. We set those all equal to 0, and we solve. For this one, we end up with A is equal to -1, C is equal to -1, and B is equal to -2. Now, the last step is going to be to rewrite the general functional relationship between our non-scaling variables and our scaling variables with these new power constants that we found. So in this case, it's going to be sigma, the surface tension, times rho to the -1, because rho is power A is -1, V to the -2 because it's power B, and D to the -1 because it's power C. And then we set it up as a fraction and we let that equal our pi 3 term. So that is what you're going to see here, which is sigma over rho V squared D. And again, it may not be obvious right away, but this is actually the inverse of the Weber number, which is another common fluid mechanics non-dimensional quantity or group. We're going to let this equal pi 3. And again, the pi terms can be to positive powers, they can be to negative powers, they could be to a half power. So you can really rearrange them as much as you want in here. It's really about just determining the general functional relationship between each of the terms. So this is going to be our non-dimensional quantity. That is pi 3, and that is the Weber number. Now that we've determined all 3 pi groups, our last kind of step with that is to actually confirm that the pi groups are dimensionless. And this is really the point of putting all of them in these specific pi groups and finding the power terms A, B, and C, is so that the total group actually has no dimension. So I'll show you what we do for that. So starting with pi 1, which we found to be equal to D over D. Now this one, pretty straightforward. D is dimension length. D is dimension length. Anything over itself is going to be equal to 1, so we can say that is in fact dimensionless. So put a little check, dimensionless. Now for pi 2, we found this to be the Reynolds number, which is rho VD over mu. Again, taking those dimensions which we found earlier, we write all those out as one big fraction like this, and then I like to follow the same step that I do for finding the actual dimensions of each individual variable. I like to write them all as individual fractions like this. So ml to the -3, I write as m over l to the 3. lt to the -1, as we have here, I write it as l over t. L, in the numerator here, we write as l over 1, t over m. Now this Cohen can be a little bit tricky sometimes when you have negative powers in your denominator. Since these are -1, these are actually going to go to the top since it's 1 over l to the -1. So it ends up being, in this case, t over m, like that, and l over 1. Now, I could have flipped it and wrote it as l here over m and wrote t by itself over 1. This just makes it easy for canceling the terms out. We're not actually doing anything specific with it. It's mostly just to check to see that it's dimensionless. But when you have them set up like this, it's really easy to see which terms cancel. So we can see right away we have L, L, and L. We got 3 L's in our numerator, and we have an L to the 3rd in our denominator. That is going to go to 1. We have an M, and we have an M. That's going to go to 1, and we have a T, and we have a T. That's going to go to 1. And the ones here and here, those are also 1. So our total dimension here is 1. That is dimensionless. So say, check, we got that one. Now, finally, we have the pi 3 term, which we know is the Weber number. It's rho V squared D over sigma. We do the same steps. We write out all of the individual dimensions, and then we write them as single fractions like this. And again, you don't have to follow this last step. This is just something I find to keep everything orderly, because if you're dealing with 3 or 4 pi groups, it's a lot of dimensions, and it can be easy to make a mistake in the algebra, and that'll actually throw the whole problem off. So for this one, we've got an m here, we've got an m here. Those are going to go to 1. We have a t squared here, a t squared here. Those are going to go to 1. we have an L to the 2, and we have an L, that's L to the 3. We've got an L to the 3. That's going to go to 1. And the 1, that's already 1. So this total has a dimension of 1. That's dimensionless. So now we found these 3 pi groups, pi 1, pi 2, and pi 3, and they all are dimensionless. Our last step is going to be to rewrite the functional relationship, which we found in step 1, in terms of our new dimensionless quantities. And the general setup looks like this. Pi 1 is equal to some function. Again, we don't know necessarily what the function is, but it is a function of pi 2 and pi 3. And this would extend on if we had a pi 4, pi 5, etc. This, we're going to rewrite it here in terms of the actual variables. So pi 1 is lowercase d over d. That is going to be equal to some function of rho v d over mu, comma, rho v squared d over sigma. So we can actually say that pi 1, or d over d, is equal to some function of the Reynolds number and the Weber number. So that, in short, is how you solve a Buckingham Pi theorem problem. Now, from this point, some problems will ask you to find things like dynamic similarity, but once you have them in dimensionless groups like this, it can be very easy to make comparisons, to solve for, let's say, a model that is not to full scale, maybe a 1/5 model. And that's what these pi groups allow you to do, is to compare, let's say, a scale model to a full size model. So I hope you liked it.